Okay. Okay, so let's look at question 1, which is saying convert the following temperatures to its values in Fahrenheit and the Kelvin scales. Convert the following temperature to its values in the Fahrenheit and the Kelvin scales. And they've given us negative 40 degrees Celsius. They've given us negative 40 degrees Celsius. So this is in degrees Celsius, and they want us to convert this value of temperature to its values in the Fahrenheit, but also the Kelvin scale. So what are we going to do? I'm sure this is very simple because if we've been given temperature in degrees Celsius and we want to convert that temperature to degree Fahrenheit, which formula do we use? Which formula do we use? Okay, so we say the temperature in Fahrenheit will be equal to the temperature that we've been given in degrees Celsius multiplied by 9/5, like that, plus 32. This is the formula that we use to convert your temperature in degrees Celsius to the temperature in degrees Fahrenheit. So since they've given us negative 40, I'm going to plug negative 40 into this particular formula. So I'll say my temperature in degrees Fahrenheit will be equal to, I'll open my brackets, negative 40 multiplied by 9/5 plus 32, like that. So your temperature in degrees Fahrenheit will be equal to negative 72 plus 32. And finally, your temperature in degrees Fahrenheit will be equal to negative 40 degrees Fahrenheit. Your temperature in degrees Fahrenheit will be equal to negative 40 degrees Fahrenheit. Well, whereas if you want to convert your temperature that you've been given in degrees Celsius to a temperature in Kelvin, we basically say the temperature in Kelvin will be equal to what? It will be equal to the temperature that we've been given in degrees Celsius plus 273.15, this constant here. Okay, so I'll just substitute my negative 40 into this particular formula, and I get my temperature in Kelvin will be equal to minus 40 plus 273.15, and this is going to give me my temperature in Kelvin as equal to 233.15. 233.15 Kelvin. Okay, so these are the two values of temperatures. In degrees Fahrenheit, it's negative 40 degrees Fahrenheit, whilst in Kelvin, it's 233.15 Kelvin. Okay, so they want us to choose the best option from the options that we've been given, A to D. That means the closest from these that we've been given here, it's option A, which is telling us negative 40 degrees Fahrenheit and 233 Kelvin. Okay, so when using this formula, the answer did not just add the decimal places here. They just added 273. That's why they are getting 233 only. That is question 1. Let's move on to question 2. And question 2 is saying water in a tank is increased in temperature from 25 degrees Celsius to 58 degrees Celsius. The water volume increases by 0.30 liters. Find the volume of the water before the temperature increase. Use the value 2.14 times 10 to the power minus 4 per degree Celsius for the volume coefficient of expansion of water. So they've given us what? They've given us the temperature change. They've given us delta T to say it's from 25 degrees Celsius to what? To 58 degrees Celsius. This is the change in temperature that we're dealing with. And they've told us to say the change in volume. The change in volume of water is equal to what? It's equal to 0.30 liters, like that. They've given us the coefficient of volume expansion of water, which is beta. Beta is 2.14 times 10 to the power minus 4 per degree Celsius, like that. So this is what we've been given in the question. And what are they saying? They're saying we should calculate the volume of the water before the temperature increase, which means we should basically calculate the initial volume of the water before the change in volume. So for volume expansion, we know to say the formula for calculating volume expansion, we say change in volume is equal to what? It's equal to initial volume multiplied by the coefficient of volume expansion multiplied by the change in temperature, like that. We've been given everything else in this question except the initial volume. This is what we don't know. So what are we going to do? We are going to make our initial volume the subject of the formula in this particular case. So I'll divide both sides by beta multiplied by delta T, even that side by beta multiplied by delta T, like that. That means my initial volume of the water will be equal to what? Will be equal to the change in volume divided by beta multiplied by delta T, like that. Okay, so this is the formula that I'm going to use to calculate the initial volume. And we've been given change in volume, we've been given the coefficient of volume expansion, and we've also been given the change in temperature. So the change in temperature is basically equal to what? It's basically equal to the final temperature minus the initial temperature, like that, which will give us 58 minus 25, and that is in degrees Celsius, like that. So our change in temperature will basically be equal to 33 degrees Celsius. This is going to be our change in temperature. And I'm going to plug these values directly into this formula that I have here. So I'll say my change in volume, which is 0.30, divided by the coefficient of volume expansion, which is 2.14 times 10 to the power minus 4, multiplied by the delta T, which is the change in temperature, which is 33. And this is going to give me my initial volume, which will be equal to 0.30 divided by, if I plug this, or if I plug my denominator into my calculator, I'm getting a 0.07062. Okay, like that. So 0.30 divided by 0.007062, I'm getting approximately 42.48 liters. 42.48 liters, of which if I write my answer correct to one decimal place, or if I round off my answer correct to one decimal place, this is 8. So that means I'm going to have my 4 being rounded up to a 5. So basically, my initial volume will be equal to 42.5 liters, like that. So that is my initial volume. And if I check the the options that have been given, I'm sure all of us are going to agree with me to say the closest option, which is the closest to the correct option, which is 42.5 that we've calculated here, is option C. So option C is the correct answer in this particular case. Let's go to the next question, which is question 3. Question 3 is saying a 1 meter rod of silver at 0 degrees Celsius is heated to 98 degrees Celsius. Its length is increased by 0.25 centimeters. The coefficient of linear expansion of the silver rod is dash. The coefficient of linear expansion of the silver rod is dash. Okay, so basically what they want us to calculate is the coefficient of linear expansion, which is alpha in this particular case. So what are we going to say? We've been given the increase in length. So the increase in length, which is delta L, is equal to what? It's equal to 0.25 centimeters, like that. And we can convert this guy into meters. We're going to get how many meters? If I divide this by 100, how many meters are we going to get from here? I'll get approximately 0.0025 meters. This is our change in length after this meter rod being subjected to this change in temperature. Then our delta T, I'm sure you can tell to say it's from 0 degrees Celsius to 98 degrees Celsius. This is our delta T. So if I say my T final minus T initial, I'm going to get my delta T of 98 degrees Celsius, like this. So this is the information that we have. And they told us to say this is a 1 meter rod. Okay, so we also have the initial length, which means the initial length is 1 meter. What are they looking for? They are looking for alpha. So we're going to apply the formula for calculating linear expansion of this rod. We know to say change in L, which is change in length, should be equal to the initial length multiplied by the coefficient of linear expansion, which is the alpha in this particular case, multiplied by the delta T, which is the change in temperature. They've already given us the delta L. They've already given us the delta T. They've already given us the initial L. What are we looking for? We're looking for the alpha. So what are we going to do? We're just going to make the alpha the subject of the formula in this particular case. So I'll divide both sides of the equation by initial length multiplied by delta T. Even that side by initial length multiplied by delta T, like that. So that and that will cancel out from my equation. That means my alpha will be equal to the change in length over initial length multiplied by delta T. Okay, this is going to give me the change in length, which is 0.0025 meters, like that, divided by the initial length, which is 1 meter. Oh, let me just do this. The initial length, which is 1 meter, multiplied by the change in temperature, which is 98 degrees Celsius. Okay, 98 degrees Celsius, like that. So the meter and the meter will cancel out there. That means my alpha will be equal to 0.025 divided by 98. 0.025 divided by 98. And I'm getting an answer which is equal to 2.55 times 10, or 551. This is 551. 551 times 10 to the power minus 5. Power minus 5 per degree Celsius. So this is the coefficient of linear expansion. If I check my options, I'm sure you can agree with me to say the closest option to the option that, or to the answer that we've calculated is the option A, 2.55 times 10 to the power minus 5 per degree Celsius. That is question 3. Section B, which are the one-word answer questions, is saying a Pyrex glass of water with a volume of 1 liter is completely filled at 5 degrees Celsius. How much water in cubic meters will spill out if the Pyrex glass, or of the Pyrex glass, when the temperature is raised to 85 degrees Celsius? Take the coefficient of volume expansion of water to be 2.1 times 10 to the power minus 4 per degree Celsius, and the coefficient of volume expansion of the glass to be 0.09 times 10 to the power minus 4 per degree Celsius. Okay, so that is what they want us to calculate. They want us to calculate the volume of spill, or the amount of water that is going to spill out of the Pyrex as the temperature is increased. And if you remember, the first class that we had under thermophysics, before we even opened, because we started our extra lessons before we even opened, the first class that we had, I said when water, or there's a liquid that is contained inside a solid container, then you reach a point where that liquid is spitting out of the container due to the temperature increase. It's just because of their differences in the coefficients of volume expansion. The volume expansion of water is higher than the volume expansion of the glass. That means water is going to expand at a higher rate than the glass that we have here. So you can tell to say we've been given the similar volume of water and the Pyrex glass, because the Pyrex glass is completely filled initially. So which means the volume is the same. But since water is going to be expanding at a faster rate than the glass that we have, you're going to notice to say water is going to start spilling out. So that means we're supposed to calculate the volume of spill after that change in temperature. And that volume of spill is going to entirely depend on the differences on the coefficients of volume or expansion of the two materials that we're dealing with. So what are we going to do? We've been given initial volume, V0, to say this is 1 liter. But the answer that they want us to find should be in cubic meters. So that means we're first, or we're supposed to convert our 1 liter into cubic meters. So if I convert my 1 liter into cubic meters, I'm basically going to get 1 times 10 to the power minus 3 cubic meters, like that, because I'm just dividing this by 1,000. Okay, so this is our volume in cubic meters, our initial volume. Then we've been given the coefficient of volume expansion of the water to say it's 2.1 times 10 to the power minus 4 per degree Celsius. We've been given the volume, the coefficient of volume expansion of the glass to say it's 0.09 times 10 to the power minus 4 per degree Celsius. Again, what else? They've also given us the change in temperature to say the temperature is being raised from 5 degrees Celsius to 85 degrees Celsius, like that. So that means our change in temperature is 85 minus 5, which is going to give us 80 degrees Celsius, like this. Okay, so this is the information that we have. So since our volume of spill is going to depend entirely on the difference between these two, we're going to we're going to come up with a single formula that is going to give us the change, or the volume that is going to spill out of the glass. So we're going to say our volume of spill will be equal to what? We know to say the initial formula says delta V is equal to initial volume multiplied by the coefficient of volume expansion multiplied by the change in temperature, like that. But since we are dealing with the volume of spill, we can just put this in a single formula to say this is going to be equal to the initial volume multiplied by what? Multiplied by the difference between the two coefficients of volume expansion. So the coefficient of volume expansion of water minus the coefficient of volume expansion of the glass multiplied by the change in temperature, like that. So the volume of spill will be equal to the initial volume, which is 1.0 times 10 to the power minus 3, multiplied by the difference between the two. So I'll say my 2.1 times 10 to the power minus 4 minus 0.09 times 10 to the power minus 4, like that, multiplied by 8, like that. So the volume of spill is going to be equal to what? It's going to be equal to, let me just punch this into my calculator. Let me just punch this into my calculator. And I'm getting exactly 1.608 times 10 to the power minus 5 cubic meters. That is the volume of water that is going to spill out of your Pyrex glass. This is the volume of the water that is going to spill out of the Pyrex glass. Or if you don't want to use this route, you can just basically find the volume or the increase in volume of the water on its own and find the increase in volume of the Pyrex glass on its own, then subtract the two, or subtract the increase of volume of the Pyrex glass from the increase of and volume of the water, and it is going to give you the volume of the water that is going to spill out of the glass. As simple as that. But this is the short form of the formula that you can use. But if you don't want to go this route, you can just basically find the volume or the change in volume of the water on its own, because we have these parameters, and find also the change in volume of the glass on its own. Then what are you going to say at the end? You're going to say volume of spill will be equal to the change in volume of your water minus your change in volume of the Pyrex glass. And this should still give you the same answer, to say 1.608 times 10 to the power minus 5 cubic meters, like that. So that is section B, question A. We can go to the next question, which is saying 3 amp current which passes through a 10 ohm resistor for 30 seconds generates heat which is used to evaporate 17 grams of water at its boiling point. What is the specific heat capacity of the water? What is the specific heat capacity of the water? Okay, so we solved this this type of a question before, and it's a very simple question because they are telling us to say there's this current that is passing through this resistor, and it is doing so for 30 seconds, and in so doing, it is generating Q, which is heat energy. So they want us to find the specific heat capacity of water if it is evaporating 17 grams of water at its boiling point. So how do you think we're going to go about this formula or this question? The only thing that we're supposed to resolve here, I think, is mass, because mass has been given in grams. And we should convert this into kilograms. This is going to give us 1.017 kilograms, like that. 0.17 kilograms. Okay, so the first thing that we're supposed to do first is find the heat, the energy that is produced, the electrical heat that is produced. And we said to calculate Q, which formula do we use? We use the formulas for electricity. In order for you to calculate the amount of heat that is generated, you're going to say current squared multiplied by resistance multiplied by time. This is going to give you the amount of heat. Okay, so I was just explaining to say, in order for us to find the heat energy, we're going to say this is equal to the current squared multiplied by resistance multiplied by time. That's why they gave us all the necessary information that we needed in the statement here. So my Q, which is the heat generated, will be equal to what? Will be equal to 3 squared multiplied by the resistance, which is 10 ohms, multiplied by the time, which is 30 seconds. And if I plug this into my calculator, I'm basically getting 9 multiplied by 10 multiplied by 30. That means my Q, which is the heat generated, will be equal to 2,700 joules. So the amount of heat that is generated by this appliance here is equal to 2,700 joules. So what are they? What do they want? They want us to calculate the specific heat capacity, and we know to say the amount of heat that is absorbed to evaporate a certain amount of a substance is equal to what? Q. Using the formula for specific heat capacity, we say Q is equal to what? Is equal to mass multiplied by the specific heat capacity itself multiplied by the change in temperature. This is the formula that we use to calculate the amount of heat that is absorbed or the amount of heat that is released, depending on whether the substance is cooling or is heating up. Okay, so from this, we have calculated the heat energy. We know the mass, it has been given in the question. they've told us to say we should calculate what? We should calculate the specific heat capacity. So what are we going to do here? What are we going to do here? What do you think we'll do here?
Make C the subject of the formula.
Okay, make C the subject to the formula, which means I'm going to divide this side of my equation by m multiplied by delta t, even that side by m multiplied by delta t, like that. Okay. So I'll say my specific heat capacity will be equal to the thermal energy that is absorbed divided by the mass multiplied by delta T, like that. Okay, what are we missing in our equation? Or what else is missing?
It's temperature, the change in temperature.
Okay, the change in temperature. So they've told us to say this question is saying the current in the resistance for this time is used to generate heat, which is used to evaporate 17 grams of water at its boiling point. What is the specific heat capacity of the water? Okay, so I'm noticing, this is when I'm also noticing to say what is missing here is the change in temperature. They've told us to say at its boiling point. We know to say the boiling point of water is 100 degrees Celsius. But the way they've asked this question here, if we are evaporating the water at its boiling point, they were not supposed to ask for the specific heat capacity here. Oh, so I'm just breaking down this question based on the experience that I have. I've seen a lot of these questions. If they are talking about evaporating water at its boiling point, they were not supposed to ask about the specific heat capacity of water, but rather they were supposed to ask about the latent heat of vaporization of the water. So from here, my conclusion would be that they made a mistake when typing the question, or it was a typing error. Or if it's not a typing error, that means we can continue with this same formula. We're just going to say this is equal to 2,700 joules here divided by the mass, which is 0.017 multiplied by change in temperature, like that. So you would divide your 2,700 by what? By 0.017 multiplied by delta T. So I'll say my specific heat capacity will be equal to 2,700, like that, divided by 0.017 delta T. We can leave it like that. We can leave it like that, or if not, that means there was an error when asking this question or when phrasing this question, because if they're asking about specific capacity, it was so unnecessary for them to start giving us the at its boiling point, blah blah blah. They were supposed to give us the change in temperature. Or if not, we can just leave it as an expression. The specific capacity of water will be equal to 2,700 joules over 0.017 multiplied by delta T, multiplied by delta T. So from my experience, I'm just telling you to say from what they brought in this question, from what they're asking about in this question, the correct question was supposed to be what is the latent heat of vaporization? And if we wanted to calculate the latent heat of vaporization, we would have simply done that, because we know to say what? The amount of heat that is absorbed to evaporate water at its boiling point is equal to what? It's equal to mass multiplied by the latent heat of vaporization. Divided by mass, divided by mass, that means my latent heat of vaporization is equal to what? It's equal to the amount of heat that is absorbed divided by the mass. And from this, we would have been able to calculate the latent heat of vaporization. We just say 2,700 joules divided by 0.017 kgs. And this was going to give me my latent heat of vaporization as equal to 158,000 or 800. This is 800. 823 23.53 joules per kg, like this. Is there anyone with a question here, or anyone who is confused? Any question or any clarification where needed? Anyone with a question, or we can proceed? Okay, so if there is no question here, we can move on to the next question, which is about thermodynamic processes. Okay, so they're saying as the gas sample was taken through the thermodynamic process represented in the figure below from state A to state B. So we have state A here to state B there. If the gas releases 5.40 times 10 to the power 5 joules of thermal energy, calculate its change in internal energy. Calculate its change in internal energy. And from what I remember, we solved this exact question in the tutorial sheet on Tuesday. This is the exact question that is in tutorial sheet 5, and we solved it on Tuesday. So how do we go about solving this question? We know to say in order for us to calculate the change in internal energy, we have to use the first law of thermodynamics, which says the change in internal energy is equal to the amount of heat that is absorbed minus the work that is done. This is the formula that we use to calculate the change in internal energy. They've already told us to say the gas releases 5.40 times 10 to the power 5 joules of thermal energy, which means what are we supposed to do here? We are supposed to calculate the work that the gas does. The work that the gas does. So how are we going to calculate the work that the gas does? We know to say on a PV diagram, the work or the area that is under the graph is equal to the work that is done by the system or on the system, just like that. It depends with whether it's expansion taking place or it's a compression. Okay, so how are we going to calculate the area under this graph? I explained this exact question. It's the same question. They've just brought it again here on Tuesday. How are we going to do that? We have the first parameters, which means initially the pressure was what? The pressure was 1 times 10 to the power 6 pascals. This is what they are telling us. Whilst the volume was equal to what? Was equal to 4 times 10 to the power, this is minus 3 cubic meters, like this. Then the final parameters from at B, the pressure is what? So this is 1, 2, 3, 4, 5. Okay, so 1.1, 1.2, 1.3, 1.4. So the pressure is 1.4 times 10 to the power 6 pascals. Whilst the volume is equal to what? The volume is equal to 1 times 10 to the power minus 3 cubic meters, like that. So how are we going to calculate the change in volume, or rather the work done? How are we going to calculate the work done? We said the work done is equal to the area under this graph. So if this is a linear process, how do we calculate the work done? I was explaining this exact question on Tuesday.
We
Anyone?
use the area of a trapezium.
Okay, area of a trapezium. Very good. Area of a trapezium. Anyone else? Is this to the power 5 or to the power 6? This is to the power 6, all right. I thought I'm making a mistake. Okay, area of a trapezium. Anyone else? So said simply, we're going to say the work done will be equal to what? It will be equal to the pressure at point A plus the pressure at point B plus the pressure at point B divided by 2 multiplied by the volume at point B minus the volume at point A. This is the formula that I told you to say you have to master this formula because it is the simplest form of the formula that we can use if you are having a linear process, a linear thermodynamic process like this one that we have here. So my work done will be equal to what? My work done will be equal to pressure A. Where is pressure A? This is A here, this is B. So my pressure at A is 1.0 times 10 to the power 6 pascals plus the pressure at B, which is 1.4. Is this 1.4? I said this is 0.2, 0.4, 0.6, 0.8, 1. 1.2, 1.4, 1.6, 1.8. Okay, so this is 1.8 and not 1.4. This is the scale that we've been given. This is 1.8. So I'll write this one as 1.8. Yes, it's 1.8. Even here, I'll put in 1.8. 1.8 times 10 to the power 6, like that. I'm adding these two, then I'm dividing them by 2, then I'm multiplying them by the difference in the second volume from the first volume. So I have 1 times 10 to the power minus 3 minus 4 times 10 to the power minus 3, like that. Okay, so the work done will be equal to, let's add what is in the brackets, 1.0 times 10 to the power 6 plus 1.8 times 10 to the power 6. What else are we getting in the brackets? Anyone? So we're going to get 2.8 times 10 to the power 6 divided by 2 multiplied by, I have 1 minus 4. This is going to give me negative 3 times 10 to the power minus 3, like this. Okay, so if I divide this by 2, I'm getting 1.4. Okay, so I've run out of space, so I'll just write here at the top, or I can write here actually. I'll use my blue pen to say my work will be equal to 1.4 times 10 to the power 6 multiplied by negative 3 times 10 to the power minus 3, like that. Okay, so my work done will be equal to that multiplied by 3 exponential minus 3. Where is negative? Okay, exponential negative 3. Okay, this is giving me 4,200, negative 4,200, like that. So the work done is negative 4,200 joules. And now that we've calculated the work done, we can bring back this formula to say our change in internal energy will be equal to the thermal energy. They've already given us the thermal energy to say it's 5.4 times 10. This is 4, not 9. 5.4 times 10 to the power 5 minus negative 4,200. So why is the work negative? Anyone who can explain why the work is negative here? It's because the gas is being compressed in this particular case. The gas is being compressed, which means the work is being done on the system, and the system is not doing work itself. Okay, so to calculate the change in internal energy, what are we going to say? This gas is releasing this heat, it's not absorbing. So if it's releasing this heat, what does that mean? That means even this value itself should be negative. So instead of it being a positive, it's being released, it's going out of the system. So it will be negative 5.4 times 10 to the power 5, like that. So which means even in our formula or in our equation here, we are supposed to indicate the negative like that. Okay, so I'm going to basically have my change in internal energy being equal to negative 5.4 times 10 to the power 5 plus 4,200. That means my change in internal energy will be equal to, let me just add this. So 5.4 is basically equal to negative 540,000 plus 4,200. This is giving me negative 535,800. Negative 535,800. This was the change in internal energy. As simple as that. So my change in internal energy, if I write it here, will be equal to negative 535,800 joules. Like that. Okay. Like that. And that is the end of this particular paper. Is there anyone with a question up to this point? Is there anyone with a question up to this point? Any question? All right, so if there's no question, guys, thank you very much for attending today's class. But I also wanted to show you to say, for those who are registered, make sure to say you go to our folders, you go to our website, you check the folder for P192. This is the past paper folder. You go to P192. For your revisions for tomorrow's quiz, you go into the video solutions. You are going to find these quiz papers. So there's this quiz one, there's this quiz one, this quiz one, there's what else? Do I have any other quiz paper? Okay, so I also have this quiz one paper. All these are quiz papers, huh? This is test one, test one, test one, test one, or test two, test two, test three. This is also a quiz one paper. This is for January 2025. This is the most latest. This is also a quiz one paper. So go through these quiz papers before tomorrow's quiz. Go through these quiz papers. And also, you should also go to the tutorial sheet folder. You do the same. In the tutorial sheet folder, you go in P192. You go to January 2026 intake. And you're going to find that we have all the tutorial sheets solved. From tutorial sheet 1, this one which is written 1 point something, all the ones that are starting with the 1, that's tutorial sheet 1. The ones that are starting with the 2, that's tutorial sheet 2. 3, that's the tutorial sheet 3. 4, that's the tutorial sheet 4. So all the 4 tutorial sheets on thermophysics have been solved. Even those that are not registered yet, you can take this time to subscribe, and you will find all these materials there. So in the folder for past papers, you'll find all these quiz papers that are solved. Then in the tutorial sheet folder, you also find all the latest tutorial sheets that have been solved. So that is all I had for you today. Thank you very much for attending today's class. Have a blessed evening and all the best in tomorrow's quiz.